Okay, good morning, everyone. Thanks for coming the Nuanced Monthly Tech Talk. I'm Yu, a postdoc at Epic FIB and TM. So today I'm going to introduce our new instrumentation, Helios 5 UC, focused ion beam SEM system. So it opens up many opportunities from like elegant sample preparation and two-dimensional or three-dimensional sample characterization. So starting from the ion-solid interaction, it's a relatively complicated process. So here we break it down to four functions. Break it down its effect into four main functions when a focused ion beam hits a solid. So the first one is the imaging by collecting the secondary electrons or secondary ions. So this allows us to do the site-specific processing. And the second one is the milling by remove the materials away. This is the main function of the FIB. And the third one is the deposition to decomposing the precursor gases into volatile or non-volatile products. The non-volatile product will remain on the surface of the sample, and volatile product will pumped away by the in the vacuum system. So the fourth one is the implantation. So the energetic ions don't just stop by the surface. They will penetrate inside the material and leaves behind the like disordering vacancies and some impurity ions. And also the dislocations, which we can see in the TM image here. So, but on the positive side, the implantation can sometimes be used to tailor properties like conductivity of thin film. On the negative side, it creates a negative damage layer that we usually want to minimize in sample preparation. So with these functionalities at the focused ion beam column, combine them with the SEM column and other accessories like manipulator, gas injection systems, and multiple imaging detectors, and also analytical detectors like EDS or EBSD detector. And more important is the 5-axis stage, like tilt, rotation, and height, XY, and with room temperature or low temperature. So it allows us, so we end up with truly multifunctional FIB instrument. So this allows us to do the site-specific sample preparation, such as cross sections, TM laminar preparation, exotic sample, like atom probe needle, and the three-dimensional morphology. Besides the analytical about the EDS and EBSD analysis. So all of these functions are already possible on our current instrument, the Hydra plasma FIB, and it has four kinds of source like xenon, oxygen, argon, and nitrogen. It excels at large volume processing, and it can be done by at low temperature. So if you would like to learn more about the plasma FIB, I encourage you to watch the excellent talk by our facility manager, Paul, which is available online on YouTube. So the upcoming, the new Helios 5 UC offers a very similar functionality, but use a different source, gallium source. So this change makes it ideal for precision milling, and it's stable for the auto TM laminar preparation. So with two complementary pair of FIB systems at Epic, so now we can use the Hydra for speed and bulk milling, and the Helios 5 UC for the precision milling. So what exactly is the difference between the gallium FIB and plasma FIB? So because of the ion beam source, the gallium source is liquid metal ion source. So a strong electric field creates a Taylor cone here, and the ions emitted by a field evaporation. So the beam will have the beam has a Gaussian profile like this. It's very sharp at low current. Here it's 9.3 nanoampere. It's very sharp, but it's broadening at high currents. Well, for the inductively coupled plasma source, here we can see that the radio frequency energy will ionize the xenon or other oxygen or some other gases. And then the ions are extracted through the aperture and will form a long beam tail shape. So the feature is for this beam shape is that it keeps very sharp at high current, like here 16 nanoampere. But so the right figure shows the beam current and spot size relationship. So we can see that under below 100 nanoampere, the gallium source has a much smaller spot size than the xenon, so which is good for precision milling. While for the above the 100 nanoampere, the xenon source has a much outperforms, so it's ideal for the large volume processing using high current. Another difference is ion implantation. The left illustration shows the collision cascade of implanted ion inside the material. So I used the stream stimulation to see the trajectory of ions inside the silicon substrate, and with different like gallium, xenon, argon, and oxygen source that we usually use. So at 30 kV, so we can see that the gallium falls between the shallowest depths of xenon and the deepest profile of oxygen. So the most important is when we lower the energy to 2 kV, the difference between the xenon and gallium nearly disappears. So it falls lower than 10 nanometers. And also argon and oxygen also decreased a lot. So tuning both the ion type and accelerator voltage, we can balance the precision and minimum damage. So these differences explains why there have some difference of the ion milling behavior. So the sputtering rate, even with a similar current, the gallium shows a little bit slower, lower sput rate than the gallium because the xenon has a higher weight, and also it causes a larger damage layer compared to the xenon, as we explained for the implantation death. Specifically for the like aluminum nickel alloy, the gallium seems to localized in the defects and grain boundaries that disrupt the structural change, the structures, while xenon will almost we cannot see obvious implantation from the EDS. But the advantage of the gallium is because of its smaller beam size. So we can make a very thin and very clean surface of the laminar compared to the, like, there are many curtainous effects which made from the xenon source. So that's why it's necessary to have a gallium FIB. And so next I will introduce the new Helios 5 UC from 5 aspects: the high resolution SEM imaging and the gallium ion optics, and then the multiple imaging detectors, including secondary electron detector, backscattered electron detectors, and also other retractable detectors like and STEM detectors. And another is the analytical detector, EDS. For this instrument, we don't have EBSD. And several other accessories, which is very powerful. So the first is the extreme high resolution field SEM. It contains the monochromator, which will reduce the beam energy spread lower than 0.2 eV. And from this figure, we can see that the edge resolution can be down significantly when use the monochromator under when the voltage lower than 5 kV. And the second is the emission field. So where a magnetic field confines the electron beam, so we can get more electrons and get a better signal to noise and resolution. And the third one is the beam resolution. So we apply a bias to the stage and then reduce the landing energy of the ions hit into the surface materials. And this shows that with the same landing energy of 1.5 eV, so the higher the bias we apply to, then the confined secondary electron and backscatter electrons can be achieved. And the electron beam deceleration can be down to 20 eV for the current Helios 5 UC. So finally, with these three techniques integrated in the SEM optics, we can achieve the sub-nanometer resolution. So ideally, when you use the FIB-SEM detector, and you can achieve like 0.6 nanometer at 30 kV and 0.7 nanometer at 1 kV for the surface resolution. So the next is the ion optics. It's also equally advanced so this shows the setup of common ion optics, but with differential pumping and time of light correction, the resolution can be down to like 4 nanometer. And yesterday I got this image from our engineer, and it shows that the resolution is 3.6 nanometer at 30 kV. And also we can achieve high resolution at low kV and low current. The ion beam currents is ranged from 1 picoampere to 100 nanoampere, and the accelerating voltage is from 500 to 30 kV. So next is the multi-imaging detectors. So it provides a full suite of detectors. So first is I will introduce the most conventional and most frequently used secondary detectors, ETD. So average Sony detector. So we usually use it for like low max searching and surface morphology, like this. And another is the ICE detector, ion conversion electron detector. It can be used as a complementary of ETD detector because they locate in different positions. So it shows inverse brightness contrast with for the changes here. And another highlighted detector is the secondary ion detector in ICE. So for using the secondary ion, the contrast is mainly from the composition. Besides, the ETD and ICE detectors also both have the BSE mode for phase contrast, and they are usually used as TM lambda transparency monitor because to check the thickness of TM lambda. And next is the TLD through lens detectors for high resolution imaging. So here, this image shows the palladium nanoparticles on several catalysts. And we can see a very beautiful topology of this catalyst. Well, the ICD detector is above the pole piece and sample and is best for the phase contrast to collect the backscattered electrons. So here they are the same error, so it shows only the palladium nanoparticles here, highlighted the contrast here. Another is a mirror detector that locates a little bit lower than the ICD detector. So it's many collected backscattered electrons to show the phase contrast, but it combines the morphology and the Kitze contrast here, so we can see the overall information here. And this detector is not installed in the plasma FIB. It's unique here. Then is the directional backscatter detectors. It's retractable, and we have two detectors, like angular detector and the concentric backscatter detector. So they have many parts for different purpose. So for the concentric backscatter detector here, the inner rings for the contrast and outer rings for topology information. And last is the stem detector below the sample. So it's similar to the TM. So we can use annular detectors, outer rings for the hard diff imaging and inner rings for the bright field imaging. So it fills the gap between the SEM and the TEM. So you can check the quality of your laminar sample before you conduct the TEM observation. So the EDS detector is another upgrade. So the sensor size of the EDS detector is 170 millimeter square. So it allows the high count rate and high sensitivity detection. And the energy resolution reaches 40 eV at the carbon K-alpha line. So it's good for detect light elements. And combined with the upgrade software, it provides much more accurate quantitative and qualitative analysis. So then is the accessories. So the first I want to highlight is the multicam, which are capable of depositing the platinum, tungsten, and carbon. So I was usually asked to which source I should use for my sample. So there are several differences for the regarding the contrast and deposition rate and the granular or amorphous structure is deposited. Another is the easy lift. We can here shows the manipulator, so we use it to lift our sample and attach to a grid. So it has a full control of 330 rotation and XYZ directions. And you can easily move the manipulator just dragging your mouse like XYZ direction inside this area, Z height direction along this area, and the rotation. So besides, you can also just use the step moving or jog moving by click the arrows here. And then is the integrated plasma cleaner to ensure a clean specimen surface before you do any processing for a sample. And the next is a charge neutralizer. So it can minimize the charge up by using electron source. So this image shows the effect of the charge neutralizer. Without the neutralizer, we can see the drifting sample drift lifts cause the non-stable deposition, while for the with the charging equalizer is very stable. So the one of the main application is the TM laminar sample preparation. So the workflow goes the deposition first, because the energetic ion will penetrate inside the material to change the structure and to damage our sample. So we need optional the electron beam cabin layer. So if you care about the top like 50 nanometer surface structure, then you should use this one, the electron beam cabin layer, and then use the relative thicker, like 1 to 2 micrometer ion beam cabin layer to protect the damage from milling. And then we can make changes on both sides and do the bottom cut to just leave a bridge that supports the laminar. And the target is make a laminar with 1 to 1.5 micrometer thickness, and the depth almost 6 to 10 micrometer, depends on your purpose. And then we can use the manipulator to lift out and then attach it to a grid. Here I shows the side of the grid. You can also attach it on the top of the grid, and using about 0.5 micrometer welding layer. So finally, we can milling the lifted out laminar, and so use 30 kV to below like 100 nanometer, and use low kV to polishing to make it thinner and less have less damage layer. So it's a complicated process, but AutoTM5 will this software will go further because it saves our time and energy. So it separates the steps into 3 parts: the chunk mill, lift out, and thinning. So the chunk mill can be fully automatically conducted by the software, and it can do the multi-site processing. Well, for the lift out, you just need to simply to guide the software that where you want to locate your laminar, then it will do all the things. And for the normal top-down thinning that we usually do, so it also can automatically done to the specific thickness. But so, but if you want to make sure the success, so please know your sample very well and optimize the parameters first before you try. Not only the 2-dimensional sample preparation, we can do the 3-dimensional characterization. So here shows use the software AutoSize and Wheel5 to how to do the 3D characterization. So first we need to isolate the target volume to make by making changes around and fiducials for alignment. So there are several ways to do the 3D tomography. The block face in the bulk material, so like as shown in this image, and also chunk lift out to lift out the whole bulk sample and remove to other substrate, and also 0-degree tilt, so you don't have to like tilt to mill the sample. Then use the auto slice and view to like do the serial milling and imaging. The software will do the automatic alignment, like autofocus, auto stigma, and the beam position alignment. And also we can use multi-imaging. Like here I used 2 detectors, the TLD and ICE detector here. And also you can add the EDS detectors to do the EDS analysis for each slice. Then we can get a stack serial images for 3D reconstruction. And there are several software that you can do for 3D reconstruction. The Avzone, we have license at Nuance, so you can use it free. And Dragonfly is open source and microscope image browser. So this is the example I used FIB-SEM to reconstructed bone cell structure. And here I show the how to use the FIB-SEM to reconstruct the structure. So because since we get the stack images from the FIB-SEM, so it can be like multiple formats like TIFF, JPEG, PNG, and BMP, and others. So all you have to do just select the images you got and then confirm the slice thickness. And the advantage of this software is that here you can see we can launch the dual beam 3D wizard, which is very helpful for our serial images that we got from the dual beam system. So after that, here the 3D wizard, dual beam 3D wizard will help you do the like tilt compensation and denoising, cropping, and anything that you have to do before the further just for image processing. So then you can do the segmentation, and you here you have many tools to segment to color the different faces, like automatically the thresholding, the markers, and the AI assisted tools. And finally, you can visualize your 3D structure and export the image or movie to show the slice-through visualization, and it can like rotate, move around a specific orbital path, and you can add scientific bars on the movie. So okay, in close, this we have two instruments in our in Epic FIB. So if you want to do the large volume like bulk 3D tomography, rapid change, and you don't want many implantation for the materials, and if you want to use the specific answers like oxygen, argon, or nitrogen, then you definitely can choose the hydroplasma FIB. But if you want to do the high resolution nano processing, like TM laminar atom probe sample, and you want to see the delicate nanostructures, nanoparticles in 3D-dimensional, then you want to get the fast and accurate EDS, then you can choose the Helios 5 UC. And this instrument will be available soon in September. If you'd like to use the facilities, please apply the training and reserve book sessions through our new course system. And if you have any questions about either FIB instrument, please feel free to reach out to Paul or myself. We are happy to work with you. And just an advanced notice that we will have a workshop and demo in October for both facilities. So please look forward to it. And thank you very much for your attention. Thank you very much.